The first chi-square test we're going to look at is the chi-square test of goodness of fit. The purpose of this test is to test if an observed distribution of counts is significantly different from a hypothesized distribution. In this test, we have one categorical variable from one population. That'll help us to distinguish this test from the two other chi-square tests we're going to look at. The conditions for this test are that, number one, the data are counts. It might seem obvious that the data are counts, but you should inspect your data and make sure that they are. Sometimes averages or proportions might be disguised as counts, and you can mislead yourself into using this test when you shouldn't. Secondly, we should have a random sample if we want to draw conclusions from the sample to the larger population. Sometimes we don't want to do that, and sometimes we don't have a random sample, but we just ask ourselves if the distribution that we're seeing is significantly different from what we would expect to see. Thirdly, all the expected counts have to be greater than or equal to 5. And fourthly, the sample observations have to be independent. Now, the typical way to check that is to see if the sample is less than 10% of the sample size, and if that's the case, then we can usually go ahead. You might also look at the particular situation and determine if the sample observations are likely to be independent or not. The chi-square statistic is the sum of O minus E squared divided by E. These expressions are the components of chi-square. We calculate one of these for each category in our data. The degrees of, and then we add them all up to get the chi-square statistic. The degrees of freedom are equal to the number of categories minus 1. On the calculator on the TI-84, this test is available. It's Stat Test D, chi-square goodness of fit test. This is not available on a TI-83, however, but you can do it with lists. And here's a brief summary of how to do that. Put the observed counts in list 1, the expected counts in list 2, calculate the components of chi-square, L1 minus L2 squared over L2, store that in list 3, and then sum up list 3 to get the chi-square statistic. At that point, you have to go to second vars and the distribution menu and look up chi-square CDF. Then you put in your chi-square statistic, a large number like 999, and the number of degrees of freedom, and that's how you get your p-value. Here's an example of how the chi-square goodness of fit test works. A certain kind of candy comes in 5 fruit flavors: lemon, lime, orange, strawberry, and grape, with about 60 pieces in each package. The manufacturer says that each flavor makes up 20% of the total number of pieces produced. But due to the way that 5 flavors are mixed together before packaging, the count of each flavor in any particular package will be random. Suppose you buy a random package of this candy and count the number of pieces of each flavor, as shown in the table below. Are your counts significantly different from a uniform distribution? Well, here are the 5 flavors. Here are the observed counts. We have a total of 60 pieces of candy in the package. Now, the manufacturer says that 20% of the candies, each flavor makes up 20% of the total number produced. Well, 20% of 60 is 12, and that's how we count the expected counts. How we figure that out: we multiply the percentage or proportion that each flavor makes up times the total number of observations, and 20% times 60 is 12, and of course those add up to 60. And over here we have the components of chi-square. We take 8 minus 12 and square it and divide by 12. We get 1.333, etc. And then the chi-square statistic is the sum of all those values in that column. Now, the hypotheses that apply in this case are the null, that the proportion of lemon, lime, orange, strawberry, and grape candies is equal to 0.2. They're all equal to 0.2. The alternative is that at least one of these proportions is incorrect. Now, this isn't what they call a multi-sided alternative. It's fairly open-ended. This statement up here, the null hypothesis, could be wrong in any way. Perhaps 2 of these proportions are incorrect and the others are all right. Maybe they're all wrong. We don't know, but the alternative would encompass all of those possibilities. The The conditions are that the data are counts. You can see by inspection that they are. The sample's random due to the nature of the packaging process and the randomness, the random selection of the package. All the expected counts are at least, well, they're all 12, so they're all at least 5. And the sample observations are independent. This sample is much, much, much less than 10% of the population. When we calculate the chi-square statistic, 8 minus 12 squared divided by 12 plus 18 minus 12 squared divided by 12, etc. adds up to 6.833. On your AP exam, if you have to produce a chi-square test, I would recommend that you at least write a couple of these to show how the components were calculated and then show the total. You might not necessarily have to write them all out. The degrees of freedom are 4. The probability that we're going to get a chi-square statistic greater than 6.833 with 4 degrees of freedom is about 0.1450, and in that situation we would fail to reject the null hypothesis. So I write my conclusion: I fail to reject the null hypothesis that each flavor makes up 20% of the total number of pieces of candy produced. I fail to find sufficient evidence that the distribution of flavors is not uniform.